Afternoon, everyone. I'm Ryan. I'm part of the reactive plasmonics team at Imperial, and I'll be discussing some of the work we've been doing on alternative plasmonic materials, looking at the applications in nanoscale heat generation, photoacoustics, and thermometry. So we're interested in alternative and specifically refractory plasmonic materials for a couple of different reasons. Firstly, we can use the refractory materials in order to improve the performance of existing plasmonic devices that operate at high temperatures. And secondly, we can make use of the losses from these materials in order to generate and deliver heat on an incredibly precise nanoscale. So this has applications in high density data storage, photothermal nanotherapeutics, and on the thermal control of different biological processes. So as part of the work we've been doing at Imperial, we've been benchmarking alternative materials to gold and silver in order to identify what could be suitable and viable alternatives. And the reason we're looking at alternatives to the noble metals is because although they have low losses, which is ideal for plasmonic applications, they have poor temperature stability, limited spectral tunability, they're expensive, and they can't be integrated with existing CMOS fabrication processes. So we've assessed a range of different refractory metals, transition metal nitrides, and conductive oxides in order to identify what could be viable alternatives. And the way we've done this, we collected spectroscopic ellipsometry data for these materials, combined it with knee theory, and generated a range of figures of merit, which would allow us to quantify which material was most suitable for various applications. So as an example, we look at photothermal nanotherapeutics. We see of the materials that are non-toxic within the body, titanium and titanium oxynitride deliver the largest temperature change upon illumination with the same power laser. So these are materials that we potentially take forward for cancer treatments in the future. In addition to this theoretical benchmarking, we've also been verifying these results experimentally. So with thin films of the refractory metals, noble metals, nitrides, and oxides, we assess the temperature stability and also their spectral tunability. And this was published in Optics Express recently. In addition, we've been developing our in-house patenting capabilities in order to assess the properties of these materials on the nanoscale. Because needless to say, the nanoscale properties will vary significantly compared to the thin film properties. As an example of this, we've been looking at the temperature stability of titanium nitride in comparison with gold. We've done this in a sequential annealing study and collecting the optical properties of these materials with cathodoluminescence. And this will allow us to define and optimize a process window in order to target specific applications. So for example, with HAMR, we would be looking at a wavelength of operation of 850 nanometers and temperature stability of greater than 450 degrees. As a brief summary of some of the results that we've obtained from this so far, we found that the gold nanodiscs degraded at 300 degrees, while the titanium nitride discs retained their shape up to 600 degrees. However, we do see spectral changes for both gold and titanium nitride from 200 degrees. And we think this is due to oxidation of the titanium nitride. So we're looking to include an oxidation barrier within these materials. In addition to benchmarking the properties of these materials, we're also aiming to measure the heat generated upon illumination of these materials. We've been looking at measuring the temperature of nanoscale plasmonic materials using photoluminescence. And this method has been developed in-house, and it's something that could be competitive with infrared bolometers for remote temperature measurement, because we're operating in the optical regime, we're below the diffraction limit, and we have a reduced measurement time. We've also been looking at photoacoustic applications, so aiming to combine optical control of acoustic phenomena. And the way we've been doing this is upon heating a plasmonic particle, we generate heat, and that heat is transferred into the substrate, and it travels through the substrate as acoustic waves. And we can measure these acoustic waves, as you see in this graph on the bottom right. And this measurement would allow us to assess the efficiency of heat transfer and dissipation between two different materials. And this optical control of acoustic phenomena will also allow us to develop photoacoustic devices. So for example, we could look at SAW devices, transducers, or metasurfaces, just to name a few. And I'd be interested in discussing this more with you in the discussion about potential applications going forward with this. Thank you very much for your time. Bye.
Good afternoon. My name's Luke Nichols, part of the research team at King's College London. I'll be continuing on the thermal theme, but this time talking about electron temperature and its manipulation in plasmonic nanostructures and metamaterials in order to control their optical properties for various applications. Electrons in a metamaterial have an associated or characteristic temperature that's associated with their energy. If we illuminate a metamaterial with an ultra-short intense laser light pulse, the electrons in the metamaterial can increase in energy, and so their temperature increases. And this can happen over sub-picosecond timescales and can increase by thousands of degrees Kelvin. This temperature then decays and relaxes back to room temperature over a course of a few picoseconds. This energy is lost to the lattice and so increases the temperature of the material. But this happens very slowly, or at much slower timescales, and only increases by a few tens of degrees Kelvin, and so there are no material changes like melting or damage to the sample. These changes in electron temperature cause strong changes in the optical properties of metamaterials. This deviates from the usual rule of thumb with nonlinearities, in that the faster a nonlinearity modulates, usually the weaker the response. In metamaterials particularly, and nanostructures, we can create fast and strong nonlinearities in order to exploit these for a multitude of applications that I will discuss later. The first application that I want to discuss is the control of the polarization of light. This scheme uses the nanorod metamaterial that was discussed earlier, and uses a particular property of the nanorod metamaterial, that it is strongly anisotropic, which means that light transmitting through this material changes its polarization state. If we use a second control light pulse, we can change this electron temperature that I discussed earlier and change the optical properties such that this anisotropy changes in strength, and thus a signal light pulse switches its polarization state when we have the control there or we don't have the control there. We show that we can rotate the polarization ellipse by more than 60 degrees over the course of a few picoseconds, and the amount that this rotation occurs is controlled by the power of the control light pulse. This has applications for ultra-fast polarization control in optical communications and chemical analysis and manipulation. This all utilizes a metamaterial, as we discussed, which has thickness of only 400 nanometers, which means that we can integrate this device with various nanophotonic devices. We also report order of magnitude better modulation speeds compared to commercial Pockels cells and Faraday rotators, which also have length scales of 10 centimeters and so are not easily integratable into nanophotonic devices. The active area of the metamaterial is macroscopic, and so we can create 2-inch wafer size devices. And also, the strength of the anisotropy of this metamaterial is 5 times stronger than any naturally occurring material, which is usually used for polarization control. The second application I wish to discuss is the control of the distribution of electron temperature in nanostructures. If we look back at the nanorod metamaterial, by changing the control light wavelength, we can change the position of hotspots of electron temperature in the nanostructure itself. This greatly affects the switching dynamics for a signal light pulse and can create both fast and slow switching speeds with the same device. This has an inherent speed advantage over commercial fiber optic switches, but also a versatility advantage in the fact that we can change this switching speed. Also, the fact that we can change the local electron temperature in a nanostructure means there's possibility for controlling this electron temperature for chemistry and catalysis. Further, the fact that we can make this device over wide area array, so up to 4-inch wafer chip sizes, we can produce hundreds of these switches with the same chip, which is not seen in commercial devices. Briefly, I want to discuss copper sulfide nanoparticles and thin films, which offer a cheap alternative to traditional plasmonic materials such as gold and silver. Copper sulfide has a favourable plasmonic response in the infrared, and not only has a cost advantage when comparing with traditional plasmonic materials, but also offers faster heating and cooling times of electron temperature when illuminated with an ultrafast laser pulse. For more details, please see the poster by Anton Bykov. Thank you for listening to my whistle-stop tour of electron temperature studies that we have conducted. I look forward to discussion afterwards on where these ultra-fast switching speeds can be put to good use, and also any potential hurdles that people can see in bringing this technology to a commercial setting. Thank you.